you guys back to is what we call radians. And radians are what a lot of the upper level math stuff is built off of, kind of like how the rest of the world uses the metric system. This is kind of like the math metric system, if you will. Does that make any sense? Because metric is, anyways, whatever. What we're going to look at here to start with is what we call how you graph angles. Probably didn't know existed. So let's look at something very simple. Let's look at a graph, and we're going to do an angle of 150 degrees. And we're going to graph that. And we graph 150 degrees, it's a positive angle. There's no negative sign in front of it, right? So we graph positive, we always graph going counterclockwise. So to start with our little graph, remember this is your 0. When they say graph in standard position, you will always start at 0. I have never seen a graph of an angle start not at 0. That'll be what you call your initial side. So the initial side of the angle starts at 0. The one ray would be here. The other angle comes up past 90. This is 180, 270, back to 360. We're okay with that, right? I think we've done this before. 150 comes up and around and stops about here, correct? This is called the terminal side. That's where the angle stops. All right? And that angle at 150 degrees stops then in what quadrant? Second. So I just wanted to get you guys the idea of remembering the quadrants. So you got Q1, Q2, Q3, and then Q4. Huh. I just realized that QI is the only word that you usually wind up spelling the word in front.
It gets you a lot of points.
Yeah, you get a lot of points if you get that triple.
Also, if you do ZA, it's a good one. Tally.
Yeah, we did some
H&G practice in history, and that word was like the main point in the reading.
Now, when we talked about what we called reference angle stuff the other day, we were talking about this stuff, and we're looking for that ambiguous case within the law of sines, where you had that same amount of angle measure off of the x-axis. And I want to get you guys kind of in the habit of finding the reference angles every time you graph an angle. It's good practice because it's going to get you really good at trading when you don't use calculators and stuff like that real fast. So how far off is 150 degrees from the x-axis? 30. So it has a 30-degree reference angle. Okay? It has a 30-degree reference angle. The reference angle, just for a quick note here, and we kind of defined it before. Is how far you off the x-axis. Oops. Why would it work there? There's an S there. Screw it. So it's how far you are off the x-axis. Your reference angles are always going to be positive acute angles. Always. Okay.
We see it there. You said reference angles are always going to be what?
Positive acute.
Why does it not sync to part of the screen?
I don't know. There's something's not right. I don't know whether it's static. I don't know what it's the sensors and the cameras in the corners. I'm not quite sure. I've heard that other people are having this problem. I haven't looked into why it happens. So when we're doing this, we're going to label, what quadrant are you in and what's your reference angle. Very, very simple stuff. Okay? The difference of this is going to be when you go the other direction. If I want to say I have a negative 210, and I want to plot that, the negative in front tells you just go the other direction when you're winding it out. That's all. It just tells you the other direction. It's someone asked this in third hour if we're going to have to solve triangles that have negative values of angles. We can't have a triangle with a negative angle but you can have it placed going a different direction. Just like walking backwards is a negative, I'm walking backwards, it's a negative vector, kind of. I'm still moving some distance, I'm just going in a different direction. So this one would go clockwise. That's all. And you just have to think backwards around what you have here. If this is 180, it's still coming this way as 180, isn't it? Then how much more do I go up? 30 degrees. So here is my negative 210. It's also in Q2. What's its reference angle? How far off? 30.
Oh,
How far off the x-axis?
How far off the x-axis are
I
you?
thought it was the part that didn't.
Remember, you want it to be a positive acute angle. So you're here, 30 degrees again. Your reference is 30 degrees off.
Alright.
And that's going to come into huge play about where things line up. You're going to be like, ooh, real soon, okay? Not bad, is it? No. So take a second and do the 45 and the 510. Plot the negative 45 degree, and then plot the 510. I want you guys to see what happens here. Also, tell me what quadrant they're in and what are their reference angles, if you please. Pants on your stupid earthquake trip. We're having one of those days today.
You know there are no cameras, right?
That's right. It's okay.
Remember
Didn't have to pause it.
when you told us there were cameras in those little speaker things?
Yeah, I tried to scare you. It's funny.
Still got it.
What quadrant does negative 45 wind up in? Fourth quadrant. Okay, so you can just work your way down 45 degrees. So there's your negative 45. What's its reference angle?
45.
It's 45. Very good. So its reference angle. Okay, so it's Q4. I'm trying to keep Roman numerals alive. Because it's not the end of the world if we don't. Hmm?
Oh, yeah, never mind. Still, exactly.
You obviously haven't seen all the Rockies, so again, we go into the 510. And I would put the 510 on a different sheet here because this is where a lot of this stuff, you really have to pay attention to what you're doing. We got 90, 180, 270, 360, and 0. If I'm going around 510 degrees, I'm making more than one revolution, correct?
Yeah.
I'm making more than 360 degrees, I'm still going. So what we do to graph that is we just loop it. There's 360. If I come up to here, it's what, 450? And then to go to 510 is come down another how many degrees? Okay. So there's my 510. And you told me I came down 60 degrees, which means what's my reference angle to get to the x-axis? 30. So it has a reference angle to bounce back up at 30 degrees for a reference angle. Okay? The idea here is to always remember that your reference angles bounce off the x-axis. They bounce up or they bounce down. Yes, ma'am?
Could it be the other type of x-axis too? Like,
In the first quadrant?
yeah,
Yeah.
okay.
What happens here, if you've got a first quadrant problem, and let's just say your angle's 72 degrees. Well, if that's 72 degrees, that's its own reference angle.
Oh, okay.
All right. Now, if I had 400 degrees, it's a good question. I'd have to go around 360, and then how much more up? 40. What's its reference angle?
40.
40. Does that make sense?
Yeah.
It works the same way. You're still bouncing how far you're bouncing off that x-axis. Okay. Notice in this problem here, we got up to that 450 degrees. Then we knew that we had to add 60 more off of it. Sometimes you'll use the y-axis, your 90, or your 270 help you add in what's left over. But remember, the reference is always off of X. Okay? It's always going to be off of X. That's the one thing you got to remember. Right, you guys might see that you get it. Oh, I didn't do it this way. Oh, nuts. Oh, did you do 510 yet? Okay. I forgot to do this. That's 150, correct? Doesn't 150 also have a reference angle of 30? So the 150 degree angle as well as the 510 degree angle, they shared the same terminal side. They're in the same quadrant and they have the same reference angle. That means they are co-terminal. Okay? Yes, sir?
All coterminal angles have cooled, like, they're not.
No,
the
it's
same.
just dumb luck.
Oh.
It's just dumb luck. Okay? Yeah, you're the second person to ask that.
Oh, so
So
now it's-
co-terminal is,
Coterminal is nothing more than when you have two or more angles that share the same terminal side, that are in the same quadrant, that have the same same reference angle.
so same.
It's like when you
so
start
same
adding-
quadrant, you got it right there.
Yeah. What happens is, as you're looking to plot something out, if I go into, we haven't done third quadrant much yet, have we? So let's say, for example, we're at 200 degrees. If that's 200 degrees, what's its reference angle? 20. It has a reference angle of 20 degrees. Now, what I want you to think is, if I start again at 0, I come around, there's 360, 540, and then I come back down again, I'm at 560.
So it's every time you add 360 to a
Yeah, and what happens is that coterminality is going to occur every time you get around to the same spot. Yes,
What
sir?
if you go in negative directions?
Same thing. If you go in the negative direction, if I'm going this way, if I come around to here, how many degrees do I go negatively then? Well, if I'm starting here to get all the way to here, it'd be negative 180, right?
60?
Negative 160 also has the same thing. What you're doing here is you're adding and subtracting 360 degrees to get your coterminal angles. And that's how that works. So for our original angle, notice our original angle was 200 degrees. That's within one revolution. You guys know what I mean by that? By saying it's between 0 and 360? Since it's within that one revolution, to get the two coterminals, because that's usually what they look for, you would add 360. And we got, what, 560 for that? And you subtract 360. We got our negative one, which was at what? Negative 160.
Where do we use the coterminal stuff like?
You'll see it. It's more or less going to help you to understand the reference angle. It shows you where else, what other values could you get that winds up in the same reference. It becomes more and more clear why we talk about coterminality as we get into the unit circle. Okay, this is just a little bit of the background to it. Yes, sir?
Alright.
Are you just gonna have us like adding and subtracting 360, or are you gonna have us go so far as like 720?
I'm not quite there yet, but yes. And that's why I was asking if your original angle was within one revolution, then you just add and subtract. If it is more than one revolution to start with, then you might have to subtract it twice. Let me show you. If I have a value of, yeah, here we go, 495. We'll do this one first. I have a reference, or excuse me, an angle that lies in standard position, blah, 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 that is at 495. And I'm going to graph that. I'm going to figure out what quadrant that is, get its reference angle. So if I start with 495, everybody agrees that it's more than 360, correct? So we have to loop all the way around and wind up somewhere. 360. How much do we have left then to get to 495?
90, and then 135?
135, so it gets me to second quadrant then, with a reference angle of
20, shoot.
45 degrees. I'm 45 degrees off of the x-axis. So what happens here is since I am more than 1 revolution, I take that 495, I subtract 360 to get my positive coterminal, which was at 135. And then to get my negative coterminal, I subtract 360 again. Oops. And it's negative 225. Because if you're going this direction, isn't this negative 180?
It is.
And then go up negative 45 again, and you're at negative 225. That's the idea of understanding where you're being placed with that reference angle, of knowing whether or not you're adding or subtracting that reference angle to get your coterminalities. Okay? It's weird, but it's not hard. Okay? And you'll see the real reason why we worry about these references when it comes back to this stuff here real fast. Okay? All right, sir, you're giving me. Which part? What would you like to do now?
Where do you start?
0. I was just being smart ass. You said 0 because that's where you start to count. Yeah, you always start in the x-axis positive and just work your way around if it's positive, and you work clockwise if it's negative. So in the other example there, I have the negative 60. If I graph negative 60 to get my coterminals, if it's negative 60 to start, I start at 0, I just go down 60 degrees. There's negative 60 degrees. What's the reference angle for negative 60? 60. See how it's just 60 degrees off of the x-axis? So the reference angle here is 60. Yes, ma'am?
So the reference angles are always going to be positive, and the coterminal angles should be like one negative.
Yeah. Yes, ma'am?
So like using the third line as a negative, and the reference angle do looks like the left side.
Yes.
Or the right side.
Left. Yes, yes. Always go to the close, because that way you're going to get a positive acute angle. If you went the other direction, it'd be positive obtuse. See how that works? And that's the whole idea of you're always going to bounce to the closest x-axis, and that's how these things work themselves through. All right. And then, so in this case, if I wanted to get my positive one, I'd start at 0 and go around to, what would that be? 300. If I wanted to get the negative one, I'd go around again to what?
420.
Negative 420. Very good. That's all it is. It's not bad. It's just working itself back and forth.
So this is how I understood the problem. You subtract the first angle from 360 to 135, then you subtract 360 again from the down angle.
That's it. That's all it is. Because you're always going to wind up that same terminal side. You're always going to have that, and you're always going to have that 60-degree reference angle. Okay? That's where this comes out. Which gets us to radians.
I have 60.
Gets us to radians. You have to draw that out. I'm just going to explain what a radian is, and then I'll show you how we calculate that. A radian is part of the circumference of a circle. No, don't draw that out. I'm going to show you. We're going to draw something out together here in a second. A radian is a measurement on the circle. Okay. If you're on the circle and you're going around the circle, you are talking about the circumference. Now, how do you find the circumference of a circle? 2 pi times your r. So your radius just makes the circumference get larger or smaller depending on what the radius is. But it always has that constant value of 2 pi with it. Do you agree? You may or may, what you guys, and you're the second person that asked this one. What you guys did is you used arc length. And that was distance on the circle. Okay? We'll talk a little bit about that later. I'm just looking at how do I measure what's called the radian.
Is this like a section of the circle?
Yes. Instead of being degree values, they're radian values. Okay?
Okay.
So let's draw this. This is what I want you to draw.
So is the already know it's too high?
No, give me a second. It's cheating, but you'll get over it. Yes, ma'am.
How big should it
You probably want it to be a somewhat decent size. I'm going to try and we're going to fill in a little bit here. When we get more and more into the circle, I do have a full sheet page that I give you guys to help. We spend basically a day explaining where everything comes from, and that'll be soon. I think last year when I was looking at my notes, I spent 4 days in section 13.3.
That's a lot of days.
But everything in upper level math that builds off this, you have to get. And once you get little bits at a time, you start to see, oh, makes sense. There's connections start to be made.
That's the third time I made that joke while you're still proud.
I start at 0. This is 90 degrees, 180 degrees, 270 degrees, and then 360 degrees. Everybody's okay with that, right? If I say that the circumference of a circle is the distance going around the circle is 2 pi, that means 360 degrees would have to equal 2 pi in radians, because it's going all the way around. Okay. 180 is half of 360, correct?
Yeah.
So what would that be in terms of pi?
Hi.
Pi.
It's the diameter's pi.
90 is half of 180. 1/2 pi, but we write it as pi over 2. Okay? Looking at 180 to 360. 270 is between 180 and 360. 1.5 is
What's the thing about it?
3 pi over 2. Very good. All right, now let's get weird.
Is this gonna all be true for all the radian formulas? Sweet.
Oh, wow.
45 degrees. 45 degrees is halfway between pi over 2
Pi over 4.
and 0. So it is
Pi over 4.
pi over 4. Because what's half of a half?
A half.
4. So this is pi over 4. Okay? Going between 180 and 90, halfway between those two is 135. Everybody okay with that?
Yeah.
135 has a reference angle of 45 degrees because it bounced up off the x-axis 45 degrees. 45 degrees less than 180 is 135. Halfway between 1.5 is
3 pi over 4.
3/4. So it's 3 pi over 4. See how I just, notice what happened. 1/4, 1/4, 1/4, 1/4. Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. What's this going to be?
5 pi over 4.
So 5 pi over 4. This is at 225. 6 pi over 4. 7 pi over 4. 7 pi over 4 in terms of the degrees then is what, 315?
I thought it was 3
Yeah.
5.
What's that last angle?
So we're at 315 there. Notice, all we've done here is we've cut the circle into fourths. And each one of these 4 angles, they all have the same reference angle, don't they?
Yeah.
Yeah.
Every one of those has the same reference angle. And as they start to move themselves around, if the reference angle at 45 degrees is pi over 4, well, let's just say this for fun. What's the sine of 45?
1.
No. Think of your triangle.
Oh, yes.
1, 1, and root 2. So would that be 1 over root 2?
Yeah.
Root 2 over 2, correct?
Yes.
What's the cosine of 45?
1.
Root 2 over 2. So if this is root 2 over 2 for your x and y value, bless you, what is it over here then? Negative root 2 over 2 and root 2 over 2. What is it down here?
Negative over 2.
They're both negatives. And what are they here?
X is positive, y is negative.
So, bless you. So as you go through everything, in all honesty, and then you might have heard this as people start doing more and more of the unit circle, but they have to memorize everything, you don't need to do anything. As long as you know your first quadrant, everything mirrors itself out. The only thing that changes are the signs, S-I-G-N. That's all it changes. Because you've got your positives, negative, positive, negative, negative, positive, negative. And that's how this stuff works. Okay? Before I get to the other two angles I want to look at, I want to show you guys how you convert. Because there's a conversion for radians to degrees. It's like unit conversion, dimensional analysis, the stuff you guys do in chemistry that you hate. But this is easy.
That's like
You're looking, you okay?
What's the root 2 over 2? I'm a little confused on that.
What I did here was, what is the sine value of 45 degrees? It's 1 over root 2. So it's root 2 over 2. What's the cosine of 45? It's the same thing. It's root 2 over 2. What we're going to get to in a second here, in the next day or so, your ordered pairs on the unit circle are your sine and cosine values.
Cool.
I didn't get it.
That's how it's all
So
works.
like the root 2 over 2, like that's not the number that like is predominant in all of this.
It is highly predominant.
Root 2 over 2?
Yeah. Well, don't have to worry about it right now. We're going to rebuild all of this with the ordered pairs later. I just wanted to show you guys how this is going to mirror itself through with the quarters, because the quarters are always the easiest ones to look at, because they're the same value, because it's an isosceles triangle. Yeah, I forgot what those called. Okay. We're going to come back to that. It was just a little example.
So we'll understand it.
Yeah, that's all I'm just getting at. Because you understood that positive, positive, negative, positive, negative, negative. These values are just going to mirror themselves through. So if you type in your calculator real fast, the sine of 135, it'll be the same thing as the sine of 45. If you type in the sine of 315, it's going to be the negative value of that. That's all I'm getting at. Because these guys mirror themselves through. And that's when we talked about the ambiguous case within the triangle, why this worked, because they had the same sine values in the first two quadrants.
That's nice to know.
It is, and that's why this stuff works. Let me show you how you convert, and we're going to come back to our diagram here. In order to be able to convert between radians and degrees, you have to do something very simple. You have to take a degree measure. Let's say we'll use that, well here, I have 110. If I have 110 degrees and I want to turn it into a radian, I slap a pi next to it and divide it by 180. That's it. You multiply it by pi over 180. And simplify the fraction. So you have 110 pi over 180, which gives you, no, 11 pi over 18.
You don't take like the 2 out.
What 2?
Well, if you divide 110.
Just cross out the zeros and go on with your life.
By 2, then you put back on.
Lippy did that. Swing, you heard me go there. Relax. What happened? What? I was mumbling under my breath. What happens here is the reason that your degree values and stuff are canceling them out is if you go long form. Remember when you were crossing stuff out, you're converting from like inches to miles and all that kind of stuff, your units would drop out? Notice how you have degrees in numerator and denominator? That's why the unit drops out. That's why the degrees go away. And it just becomes in radians. You don't have to write radians as far as your units are concerned. once you have something in terms of pi, it is implied that it's radian. Okay? You don't have to worry about it. And then going the other way, if we're going to go the other way, for example, a negative pi over 9, in order to convert that into degrees, I multiply it by 180 and divide it by pi. So I want the pi's to drop out.
And the
Yeah. And then you simplify it out. So the pi's drop out, you get negative 180 over 9.
20. 20.
Very good, negative 20.
Oh, you kidding?
Okay.
Okay, so the pi cancels out.
Yep. Pi over pi is 1. Yes, ma'am.
Why?
It's not negative 180, it's just 180. The original problem started as negative pi over 2. It was a negative angle.
Oh.
We're still converting it.
Yeah.
It just says it as a negative angle here. I know the book doesn't say to do this a lot, but do me a favor. When you're converting back and forth, because that's some of the stuff you're going to do tonight, find the reference angle real quick too. All right, find the reference angle. You can look at negative 20 and probably tell me what the reference angle is off the top of your head. 20 is 20. We didn't really do the radian one yet. I'm going to leave you guys on the radian. It's not that bad. Okay. Now, if we go back to our circle that we started with.
Yeah, hello.
Do you have to draw that?
No, this, I'm just going back to what we had. We already had this at, what was this, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and then 2 pi.
OCD heaven.
Okay? We're okay with that. That's what you guys already had on your circles. The only other two angles that we worry about at all are 30 and 60. So what's 30 degrees in terms of pi?
Something over.
So slap a pi next to it, divided by 180.
That makes sense. Pi over 6.
Okay, so
Pi over 6.
So you get pi over 6. So 30 degrees is pi over 6. If this has a reference angle of 30 degrees here, what's its degree measure? 150. So there's 150 degrees. Remember, if I have a 30 degree reference angle,
Yeah.
now think of it, now I want you to think in terms of fractions. In terms of sixths, pi is 6 over 6. If I move up a 6, what is it? 5 pi over 6. If I move down 30 degrees, I'm now at 210 and 7 pi over 6. See how the reference angle is bouncing it? All you needed to know was this. The rest of them, they just move up and move down off of this fraction. Okay, so what, Mama?
so is the last one 330?
The last one is 330,
Oh wait, it's
and then this one comes down to, well, think of it in terms of a whole, 2. If I wanted to have 2 rewritten as a denominator of 2, isn't that 6? Math. I'm thinking of 6s, I'm sorry. 12 over 6. So what's 1/6 less than 12? 11. Sorry, I was doing the wrong thing. Once again, if this is a 2 as a whole, and I want to deal with it in terms of a 6th, that's the same thing as saying 12 over 6 here. You guys agree? If I'm bouncing down, I'm losing a 6, so I'm at 11 pi over 6. Same idea at our 60 degree angle. 60 degrees becomes 60 pi over 180, pi over 3. I get pi over 3 there. If I come back up here into this quadrant, coming up 60 degrees, so I'm at 120, which means that instead of being in terms of a whole here at 1, I'll be at 3 over 3. If I come up a third, where am I at? 2/3. If I go down a third, I'm at 4/3.
Wait, what is that?
What angle, what's 30 plus, or excuse me, what's 60 plus 180?
Townhomes and 240.
It is, because isn't that 30 more than 210?
Oh, so it's going up by 60 each time.
Okay.
This looks like a different language.
It does, but it's not that difficult.
It
Because
really-
everything is bounced off that first quadrant. Come down a third. If you come down a third over 2 pi, what are you left with? Remember, put this in terms of 3, so wouldn't that be 6 pi over 3?
Yeah.
So you're at
6, 4, 3, 2, 3, 4, 6.
5 pi over 3, right?
So 300 equals
Think of your
5 pi.
reference angle. Your reference angle up here is 1/3, which means I come down 1/3. If this is 2, that's the same thing as saying is 6 over 3. What's 1 less than 6? 5 pi over 3.
No, but I get it because it's going like 6/3, then it's over 6, and over 4, then over 3, then over 2.
Mhm.
What, is the 180 over 1 then?
Yeah,
Okay,
because it's 1, it's a whole.
okay.
So it can be 6 over 6, 4 over 4, 3 over 3. It can be any one of them. Okay. Now here's the really big idea of what I want you guys to notice. Share the same reference angle, don't they?
Yeah.
Their y values are the same, aren't they?
Yeah.
Okay? Your y values are the same. Share the same reference angle, don't they? Their x values are the same. Right. Because they're 90-degree angles at each one of these, which means your ordered pairs just alternate. Come over here. Come over here. All 4 of those angles will have the same coordinates, but they're going to have different signs, S-I-G-N. All of their signs are going to be different. If I come through these, same idea. Same values, same values, same values, same values. It's a perfect square because all of those are going to have the same values. Same thing with the last one. As long as you learn these 3 values of sines and cosines, everything else is replicated. You don't need to memorize this out because it's all based off of this. Every one of these has its own reference angle. Identifying reference angles is key, which means some of the reference angles you guys are going to get are going to be like 20. Does 20 degrees wind up on this circle like that? No, so that you have to use a calculator. We're going to be looking at all values that are replicated upon what we call our unit circle. Everything that we deal with in terms of by hand, most of this will wind up being eventually, is that everything will be replicated off of this unit circle. You don't need to do anything else other than know what the sine and cosine is of a 30, 45, and a 60-degree angle. If you know that, you're fine. Does that make a little bit of sense? This is where this heads. This is, I really enjoy working with this stuff. This is a lot of cool stuff here. It takes it's not a real complex idea. It's just it's just such a new idea. Okay. Questions? What's that?
I like fire.
Here's what I want you to do. It's page 780. Oh, was it 32 through 58 evens, please? On some of the problems where you're plotting your stuff, saying to graph them and then saying to find your coterminals and stuff, try to get in the habit of identifying what your reference angle is as well. It just gets to be good practice, so that way when we're working with our stuff later, you'll get better at it. All right. I'll have stuff for you guys tomorrow. It's a little bit more of this, as well as how we can do more with reference. It might be a little bit of the same. Kind of look like the notes were the same. And then if I'm around Friday, we'll do something else. If not, I have something for you guys ready. It's building off the same thing. If you guys get in a jam, you get stuck on something, go talk with one of the other Algebra 2 teachers or one of the pre-calc teachers. All right, go talk to Seth, go talk to Mr. Thames, Mr. Blascota, Mr. Fontana. They'll be able to help you guys out. Yeah, Cliff.
Mr. Tassis or something, like someone like that,
What is that?